we're solving systems of equations with two variables. We're going to solve by graphing, which we have technically already done that with previous questions. We're going to solve using the substitution method. We've already done that. We're going to solve using the elimination method. You may not remember that one. I'll show it to you. Then we're going to have word problems. Yay! First of all, what's a system of equations? It is a collection of two or more equations that you're looking at the same time. So if you look at this example here, this is a system of two equations in two variables, and because the highest exponent is a 1, these are linear. The idea behind solving a system of equations is you're trying to find where the one point is that satisfies both equations. For instance, if you look here, the solution to this example, the solution is 2, -3. What they've done here is they've taken each equation and they've replaced x with 2 and y with -3, and they've shown you that when you plug it in, you get a true statement, the left equals the right, which means it's a solution. And because you get a true statement on both of them, it is the solution to the system. Does that make sense? So let's look at the first method for solving a system. You do need a graphing calculator. It would help. Okay, this slide is to show you how to solve a system of equations graphically. So if you like to highlight your notes to kind of set apart, what the difference is between the slides, this is a example of solving graphically, which means you're relying on the calculator to do the job. So before we can take this system and set it in our calculator, we need it to be in the slope-intercept form. If you look, these are both linear, meaning x to the first power. And I cannot type that in my calculator because it's not in y equals form. And if you ever think you're going to forget that, look at the button that you would push to enter an equation in your calculator. You would push the button that says y equals, which means you should have it in the form of y equals, and we don't. So let's make a note. Must be in y equals, and now I'm going to put in parentheses, which really means slope-intercept form. So we need it to be y equals mx plus b, right? So take each equation. This was our first one. Here's our second one. And get them in slope-intercept form. It's a cup game. Shuffle them around so that it's y equals a number. Or, mx plus b, not a number. Then look up here and see if yours matches mine. Now go to your calculator, go to y equals, and it does not matter which one you enter as y1 or y2. Now remember, when it comes to the test day, you need to know how to type this in the calculator. You can't raise your hand and say, I don't remember how to type this in. You've got to know that, so you need to be practicing it, okay? Go to y equals, you type them in. Now we obviously want to go to the graph. Your calculator is going to go to the same viewing window as it was last used, which we will reset our calculators that morning, so it'll go to the standard viewing window. I like to just do Zoom 6. Zoom 6 is standard, which means -10 to 10. I didn't like that. Oh, hold on, technical difficulties. My calculator's wigging out right now. I don't understand. Wow. Okay, did you see the intersection of the two lines? Did you see both of them pop up? Stand by for 1 second. Oh, there's a difference between the negative button on your calculator and the minus button. So be careful. Okay, it didn't even take. There we go. I beg to differ. Oh no. The whole thing's, oh, you know what it is? Yeah, when I pulled my calculator up, that equation was in there from before. It didn't clear it. Let me fix that. I have no clue. All right, Zoom 6. Yeah. Okay, you see they're crossing. The goal is to know where they're crossing. You need to tell the calculator to calculate the intersection. So look up here. Anything to do with graphing or statistics, plotting, stat button or up here. All of this up here. So there's calc. I'm going to hit second calc. You see intersect. And it's going to say, okay, tell me when I'm on the first curve, which is really a line. Tell me when I'm on the second curve, and then put the cursor about where they're crossing. So by default, it's going to land on one line. Just hit enter. It's going to say, where's the second curve? Hit enter. It will default and jump to the other graph. Now it wants you to place the cursor in the area where they're crossing and hit enter. And then you get the solution is 2, -3. Let's take some notes. So in the calculator, y'all all know how to enter in y equals, so I'm not going to write that part down. You're going to do second calc and then intersect. And then it's going to ask you 3 questions, and then it will produce the solution. So the solution to this system, was 2, comma, negative 3. Now, I put this graph here if you wanted to sketch it. Y'all recall how to graph a line? Begin with B, move with M. We'll get that trademark before someone tries to take it and get famous off of it. No, I never made it. I kind of like that I don't have TikTok because I would lose hours of my life on it, you know what I mean? And I don't want that. I have an Instagram, and I do Instagram reels, or I watch them, they're funny. All right, begin with B. B is negative 5. Move with M. M here is 1 over 1, so up 1, right 1. And I'm actually going to keep going until I hit the solution because I want to make sure my line is accurate. Up 1, right 1. There it is. That is the solution. And now I'm just going to try to draw a line. The other line is B is 1. The slope is negative 2, which means it's negative 2 over 1, which means it's down to right 1. So down to right 1, down to right 1. Winner, winner, chicken dinner. There's the solution. So, when would you want to solve the system by graphing? When the numbers are extremely ugly and you just want the calculator to deal with it, like some decimals or something really hideous. The only difficult part would be trying to find where they're crossing in the graph. Let's say you went and you graphed it and you hit zoom 6 and you can't see a single thing. You have to be comfortable with the calculator to play with the window, to zoom out and zoom out until you start to see where they actually go, and then adjust the windows where you can get it close enough that you could do second calc. Okay? When you're graphing, and actually when you're solving any system of equations, there are special cases. This right here is when there is one solution. This is what you're used to. It means the lines will cross somewhere. They have one point in common. The vocab behind it, and this is what is annoying in my math lab. They are going to push you to know these vocab words. The vocab behind this example is the system is consistent and the equations are independent. These are the vocab words. Let's highlight it and then I'll explain it. Consistent basically means when you're talking about graphing, solving a system, consistent means the lines cross. Somehow. They cross, they touch, somehow. These lines touch. It's consistent. They have something in common, right? Independent means they are two totally different lines, though, right? You all know what independent means. If you're an independent person, you kind of, do your own thing. The lines are totally different lines, so they are independent. Consistent's the one most people struggle to remember. It just means they cross. They definitely touched. Because enter, special case, when they run parallel, notice the word to describe this type of answer is inconsistent because they do not cross, they run parallel, which means they have nothing in common. However, they are still two totally different lines, right? right? So they're still independent, but what were the results of your solving the system? The results were inconsistent because they never crossed. So I can't tell you the answer. You know, like there's not one. It's no solution. Third special case. When you go to graph the two lines and they end up overlapping, right? So the graph looks like there's only one line graphed, but there's actually two. In that case, we would say, okay, these lines are dependent because they ended up graphing the exact same thing. They are the same line. However, did they touch? Do they have points in common? Yes. So they're still consistent. They definitely had points in common. But because they ended up being the exact same line, they're dependent. So what is the answer? Infinitely many solutions. I like this right here where it says common point. The whole consistent, inconsistent, common point. I like when things start with the same letter, and in this case, same two letters. Do they have common points? Meaning, do they touch? Yes, then it's consistent. In this case, when they're parallel, they have no points in common, so it's inconsistent, which means no solution. When they touch in a manner that the graph looks like you only graphed one line, it is still consistent, however, they are dependent because it is infinitely many solutions. They are the same equation in that case. All right, let's go to the next example. You are highlighting. We are using the substitution method here. You already have practiced the substitution method, so go. Remember, you want to look for the variable that has a positive 1 coefficient. That's the variable you want to get by itself because that'll make your life easier. You could sit here and solve for any one of those four, I say four, because you got 1, 2, 3, 4, right? You could pick any one of them. Y'all ever heard the phrase, think smarter, not harder? Y'all heard that? You want to pick the variable whose coefficient is a positive 1, because then that's less work on you. So in this case, you could go for the x to be by itself, or you could go for the y in the other equation to be by itself. It does not matter. Our work along the way will be different if we went different routes. However, our answer at the end will be the same. This is when you're taking the expression, like, so get one of them by itself. Oh, this is saying, hey, this is equation 1, this is equation 2. Yeah, this is just to help you, which would really, if you already know how to do solving by substitution, you really don't have to worry about that. That's more for when we do elimination, when it can get confusing. Yeah, you can ignore that right there if you want. It doesn't matter. All right, solve this. You should get nice answers. going to have to know how to do this. You might think, well, I can just solve this by graphing, because on the test, my math lab won't know the difference. You are going to have to put your work on paper to go along with your test if it says solve by substitution. Does that make sense? So make sure you do know how to do it. Every single one of these methods works every single time. It's just you need to know how to do all of them and then learn how to differentiate when to use each one to make your life easier. So here's where these little bold numbers come in place. I chose to solve for x from equation 1, which is why I have this right here. And I'm taking notes so that anyone that's struggling will know where my thought process was. So from equation 1, my goal was to get x by itself, which gives me that, right? Okay, so now through substitution, the idea is to get an expression for one variable and then take it and plug it into the other equation. And now your equation should have just the same variable throughout, which allows you to solve. So now I'm going to, because that was equation 1, and this is where these numbering, Mallory, this is where these numbers sometimes help. I've seen people accidentally, red means wrong, I've seen people take expressions and plug it back into itself, like, or wait, go in the X. They plug it back into itself like this, and then they get lost. So that is where the numbers sometimes are helpful, because if you just manipulated 1, now you need to plug it into 2. So let me get that off the screen. So now I'm going to take equation 2, copy it, I'm going to plug this in here for x. So 2 goes in front, parentheses, because that's more than one thing, right? Parentheses, y plus 5, bring down plus y equals 1. Clean it up, distribute the 2. Combine like terms. Subtract 10. Divide by 3. That's part of your answer. Now I'm going to go back over here and I'm going to plug that in. So x is y plus 5. Well, what is y? Negative 3. So what's x? 2. So the solution is 2, negative 3. Now let's practice the vocab words. That means this system must be consistent or inconsistent. Did you come to an answer? Like, that's a point. So this is consistent. And are they 2 totally different lines? Yeah, if they're crossing in one spot, they're 2 totally different lines. So they are independent. How do you feel about solving by substitution? Now, I wrote way more up here than what you normally would write. I did that because in case anyone, was struggling with it. Normally wouldn't have to write that much. Okay, now let's go to the one that you've not seen in a while, which is the elimination method, which is my favorite because stuff disappears. Hence the name elimination. where it's very helpful for having the little numbers like equation 1, equation 2. The idea here is if my equations have a single variable with opposite coefficients, so for instance, like right here, if you notice one equation has plus y, the other equation has minus y, you should see visually if I just stack them and add straight down, what's going to happen to the y's? They're going to go away, which is why it's called elimination, which means, yeah, go on. You're good. Which means the y's would disappear and the x's would be left in the equation, and you could solve for x. And then once you know x, then you can solve for y, and bam, you're done. I love this method because it's short and sweet. I will say it pushes you to learn how to manipulate equations. This one is very easy because from the get-go, you already have a variable with opposite like coefficients. When I say that, I mean same number but different signs. Let's take some notes. Look for the same coefficient of a variable, has to be the same variable, with opposite signs. Perfect example would be the y's here. This example is to show you what if it already starts out that way. You just need to recognize it, and you're going to come right here the way it's lined up. This is nice and ordered. Everything's in order. I'm going to draw a big old line underneath and a plus sign, and I'm going to add straight down. Those go away. I'm left with 3x equals 9. Divide by 3, x is 3. I'm going to pick equation 2 to plug it in. Doesn't matter which one you pick. I'm going to use equation 2 and plug x in. So equation 2 is x minus y equals 7. I found x to be 3. The parentheses are there just to let you know I was plugging it in. That is a positive 3. I would subtract it. Then I would divide by the negative 1. So the solution is 3 negative 4. And because we came to an answer and it's a single answer, the 2 vocab words are what? Yep. Let's make note of 2 things. The first, it's helpful when they are, yeah. It's helpful when they're in ax plus by equals c form, which is called standard form. Doesn't have to be, but it helps, I think, visually. A lot of people keep their thought process in order. Once you are ready to go, right here, what we did here with this whole line and the plus sign, we just stacked the equations, they already were, and we added straight down. So I don't know if you want to make a note that right here, we stacked, or just stack and add. How's that? They were already stacked. They already had the y variables with opposite coefficients. We just added straight down. Okay, let's level it up though, because that was too easy. Let's go to one where there's not already opposite coefficients. Use the elimination method to solve here. You will notice that in the x's we have 4 and -5, and the y's we have 3 and 2. We do not have anything we can go ahead and proceed with, so this is where you have to think to yourself, find the LCM of each variable's coefficients. So looking at x, we need the LCM of 4 and -5. Looking at y, we need the LCM of 3 and 2. LCM, least common multiple, which means if you sat down and you listed all the numbers that 4 divides into, it'd be 4, right? Starts with itself. It has to divide into it. 4, 8, 12, 16, 20, 24, 28, and so on. Now go to the list of 5s. It can be -1, doesn't matter. But -5, -10, -15, -20, -25, and so on. LCM means what's the smallest multiple that they both go into? 20, right? So right here, this is 20. The negative doesn't really matter. 4 goes into 20, 5 goes into 20. Now you find the LCM of 2 and 3. Yep. And I think, let me look. If it's numbers you're just not familiar with, if it's numbers you're not familiar with, hit the math button on your calculator. Hit the math button, arrow over to number, and then look at number 8. Arrow over, oh, I'm in the graph. Hold on, let me get out of the graph. Math, arrow over to NUM for number. Number 8, LCM. You can type 2, there's a comma, it's right here, comma 3, and it'll produce it for you. So if it's numbers you're not familiar with, or you're nervous, you maybe don't have the least common multiple right, check it in your calculator. So you might want to make a note. In the calculator, it's math, arrow over to number, and it's number 8, LCM. So you have the freedom of choice. Do we want to proceed with an LCM of 20? Or do we want to proceed with an LCM of 6? Think smarter, not harder. Let's go with 6 because it's smaller, right? Did you enter negative? You can't enter negative. You just have to enter the, yeah. No negatives. Don't enter the negative. Okay, we're going to proceed with 6. So I'm going to mark through this because we don't want to use this one. We're going to write too big. We're going to go with the LCM of 6. Okay, so the goal is, now where did the 3 and 2 come from? What variable? It came from right here. The goal, you've got to have the goal in mind. The goal is, I need that to be a positive 6y and a negative 6y, right? Let's make a note. The goal is positive negative 6 for coefficient of y. That's the goal. Remember, with equations, whatever you do to one side, you have to do to the other, and you can do whatever you want with them. So what we're about to do is completely allowable because we're going to do it to both sides. I tend to like the top equation since they're both positive already. Obviously, one of them needs to become negative. I like to let the top equation be the positive and the bottom equation to be the negative. It does not matter though. What do I need to multiply my top equation by to make this become a positive 6y? 2. So this whole equation is going to get multiplied by 2. What do I need to multiply the bottom equation by in order to get negative 6y? Negative 3. So this whole equation is going to get multiplied by negative 3. And now I'm going to do this in a manner that they're already stacked. So that way I can just go straight to where we did in the last problem. So I'm labeling my equations. Equation 1, you're multiplying everything by 2. It's going to be 8x plus 6y equals 22. Equation 2, you're multiplying everything by negative 3. Watch your signs. So the top equation, everything doubled. The bottom equation, everything tripled with a negative. Oh, yeah, no, I did. Thank you. Negative 45. I definitely saw 5. I did negative 3 times 5. This was the goal, and we just achieved it, right? So now you're ready. They're already stacked. Now you add straight down. We're going to add the whole thing. So 8x plus 15x. 23x. What happens here? And they're gone. That was the goal. That was by design. 22 minus 45. Divide by 23. X is what? And now you have freedom of choice as to which one you want to plug this into. Y'all think smarter, not harder. Do not plug that into one of your larger equations you just generated. Go back to one of the originals, because the numbers are smaller, right? Go back to plug this into an original. Doesn't matter which one you plug it into. I plugged it into equation 1. So equation 1 was 4x plus 3y equals 11. I found x to be negative 1. So that's negative 4. So the solution was negative 1, 5, which means this is a consistent system with independent lines. Here's a what if. What if you were finding the LCM of two numbers? What's the LCM of 4 and 8? 8. Remember, it's got to be the number they can both divide into. So sometimes the LCM can be one of the numbers itself. So that's okay. The point of that was just sometimes you're looking for the LCM of two numbers, and it can be one of them. All right. The next slide is an example of the two special case scenarios. I'm actually going to go ahead and do it because there's no way around it. Since they are special case scenarios, they solve fast. Because you come to either a true statement or a false statement. So let's look at this right here. Now these are, if you want to label this slide, these are the special cases. Look, we've got 1 and -2, or we've got -3 and 6. I manipulated x. What can I do to make those equations have opposite x coefficients? Multiply the top by 2. Do y'all see that? If this was a +2, x would disappear, correct? So we're going to multiply the top by 2. We would get 2x minus 6y equals 2. This is the bottom equation, right? This was equation 1, this was equation 2. What do you notice happens? Look at that. And you end up with 0 equals 7. False. Since this is false, it means no solution. Which means, what type of lines? It is inconsistent because we have what type of lines on the graph? They never cross. Inconsistent, no common points, so they are parallel. However, that means there's still two totally different lines. Let's do B. You got 2 and 4 or 3 and 6, doesn't matter which one you shoot for. I chose to manipulate x, so I multiplied. Now the bottom equation has the larger numbers, so that means the top equation I need a negative, don't I? I multiplied the top by -2. I get -4x minus 6y equals -12. Equation 2 looks like this. When I go to stack and add straight down, I end up with what? Equals, which means infinite solutions, all real numbers, right? If they're infinite, all real numbers, they're the same line. Y'all can write this tomorrow if you want. I'm going to go ahead and write it in the video. It is consistent because they do touch. However, they are dependent because it's the same line. You need to go ahead and start the My Math Lab 9-1 homework.